Hello my dear students, let us start with the next chapter, structural stability. Here we are mainly dealing with the columns and struts. Columns and struts are structural members subjected to compressive forces. And here the lengths of these members are large compared to their lateral dimensions. A structural member subjected to an axial compressive force is called a strut, or a member of structure or bar which carries an axial compressive load is called the strut. Okay, here a strut may be horizontal, inclined, or even vertical, but a vertical stress used in buildings or a frame is called a column. So generally a member in any position other than vertical subjected to compressive load is called strut, and vertical member subjected to compressive load is called column. Another difference between the strut and column is the strut may have its one or both the ends fixed rigidly or hinged or pin jointed, while the column will have both the ends fixed rigidly. The examples of struts are piston rods, connecting rods, side links in forging machines, etc. The failure of such members will occur. There are three types of failures: by pure compression, by buckling, or by combination of pure compression and buckling, depending upon the slenderness ratio. So here columns are classified mainly into three categories, that is short columns and medium size columns and long columns. First we will discuss about short columns. Columns which have lengths less than 8 times their respective diameters or slenderness ratio is less than 32 times are called short columns. What is the slenderness ratio? It is the ratio of unsupported length of the column to the minimum radius of gyration of the cross-sectional ends of the column. This we will discuss in detail in the next topic. Okay, here this short columns mainly it is based on their length and diameter it is classified. Okay, if the length is less than 8 times their respective diameter or slenderness ratio is less than 32 times, then it is called as short columns. Short columns face by crushing. Okay, that is not it face only by crushing, not by buckling. Therefore it is assumed that short columns are always subjected to direct compressive stresses only. Then let us will see medium size columns which have their lengths varying from 8 times their diameter to 30 times their respective diameters or slenderness ratio lying between 30 to 120 are called medium size or intermediate columns. Okay, here its lengths varying from 8 times their diameter to 30 times their respective diameter or slenderness ratio is in between 32 and 120. Okay, here intermediate columns face by a combination of crushing and buckling. You can see the difference. The short columns face only by crushing, but medium size columns face by the combination of crushing and buckling. In these columns, both the buckling as well as direct stresses are of significant values. The next one is large columns. The columns having their lengths more than 30 times their respective diameters or slenderness ratio more than 120 are called long columns. Okay, here the lengths are more than 30 times their respective diameter or slenderness ratio is more than 120, then it is called long columns. And long columns face by buckling. Here the failure is due to the buckling, not by crushing. Therefore they are usually subjected to buckling stresses only. You can see the difference. In the short column they mainly face by crushing. Medium columns they fail by the combination of crushing and buckling. Large columns they face by buckling. Okay, so these are about the different types of columns. Next we will see the failure of column or a strut. It has been observed that when a column or a strut is subjected to some compressive force, then compressive stress is induced. All of you know now what is stress. Stress is nothing but load divided by area. Here compressive stress, that is equal to compressive load divided by area. Okay. Now we'll see what happens in the case of columns when it is subjected to the loading. If the force or load is gradually increased, the column will reach a stage when it will be subjected to the ultimate crushing stress. Okay, when you apply the load and keep on increasing, the column will reach a stage when it will be subjected to the ultimate crushing stress. Beyond this stage, the column will fail by crushing. The load corresponding to the crushing stress is called crushing load. Okay, there is a limit till that stage. The column will resist that load. After that, it's failed by crushing. So the load corresponding to the crushing stress is called as crushing load. It has also been experienced that sometimes a compression member does not fail entirely by crushing, but also by bending, that is buckling. So bending is also called as bending stress is also called as buckling stress here. This happens in the case of long columns. Okay, it does not fail entirely by crushing. It may fail by bending also or buckling also. And it has also been observed that all the short columns fail due to their crushing. Short columns always fails due to the crushing, not due to the bending. Okay, but if a long column is subjected to compressive load, it is subjected to a compressive stress. If the load is gradually increased, the column will reach a stage when it will start buckling. The load at which the column just buckles is called buckling load or a critical load or crippling load, and the column is said to have developed an elastic instability. Okay, this is important. You should know when a load is gradually increased, the column will reach a stage when it will start buckling. The load corresponding to this stage is called as buckling load or a critical load or crippling load. Okay, for a long column, the value of buckling load will be less than the crushing load. You should remember this. In the case of long columns, what happens? The buckling load will be less than the crushing load. Buckling load is nothing but bending load. Okay, moreover, the value of buckling load is low for long columns and relatively high for short columns. Now let us see the Euler's column theory. The first attempt to study the stability of long column was made by Mr. Euler. That's why this theory is called as Euler's column theory. He derived an equation for the buckling load of long columns based on the bending stress. While deriving this equation, the effect of direct stress is neglected. He has considered long columns, so there is only the bending stress or buckling stress. So the effect of direct stress is neglected here. Okay, this may be justified with the statement that the direct stress is induced in the long column is negligible as compared to the bending stress, because the direct stress is induced is very less in the long column as compared to the bending stress. That's why it is neglected. It may be noted that Euler's formula cannot be used in the case of short columns because the direct stress is considerable and hence it cannot be neglected. Okay, Euler's theory is only for the long columns. You cannot consider it is for the short column, because in the case of short columns the failure is mainly due to the crushing, but here that effect is not considered. So Euler's theory is applicable only to the long columns. Whatever the theory is derived, have to assume some assumptions. So let us see what are the assumptions made in the Euler's column theory. The first one is, initially the column is perfectly straight and the load applied is truly axial. Okay. Second one is, the cross section of the column is uniform throughout its length. Third one is, the column material is perfectly elastic, homogeneous and isotropic and thus obeys Hooke's law. Okay, and the length of the column is very large as compared to its cross-sectional dimensions. The shortening of column due to direct compression is neglected, means here that crushing effect is not considered. The failure of column occurs due to buckling alone. Okay, these are the assumptions made in the Euler's theory. Okay, mainly the column is perfectly straight and the load applied is to the axial. Then cross section of the column is uniform throughout its length, and column material is perfectly elastic, homogeneous and isotropic. The length of the column is very large as compared to its cross-sectional dimensions, and the shortening of the column due to direct compression is neglected here. The failure of the column occurs due to buckling alone. This assumption was done. Okay. Then there is some sign conventions for Euler's theory, that is like this: if it is a moment which tends to bend the column with convexity towards its initial central line, as shown in the figure, is taken as positive. Okay, if it is convexity, then it is called as positive, and if it is tends to bend the column with its concavity towards its initial central line, then it is taken as negative. You can see here, this is the central line with the convexity towards its initial central line, then it is positive. If it is in this direction, then it is taken as negative. Okay, in different signs used for bending of columns in different books, but usually we follow this sign convention which are commonly used. Okay, next, type of end conditions of the column. In actual practice, what happened, there are a number of end conditions for columns, but we shall study the Euler's column theory on the following 4 types of end conditions which are important from the subject point of view. There are 4 end conditions. First one is both ends hinged, both ends fixed. Second condition. Third condition is one end is fixed and the other hinged. And the last condition, fourth condition, is one end is fixed and other is free. So there are many conditions are there. We will mainly concentrate on these 4 end conditions of the column. Both the ends hinged, both the ends fixed, one end is fixed and the other hinged, and one end is fixed and other end is free. Okay, so what happens, how the diagram we'll see. One columns with both the ends are hinged. You can see here both the ends are hinged. This is hinged support. So when you apply the load here, the column bends like this, right? You can see this. So this happens in the case of both the ends hinged. When both the ends are fixed, you can see here both the ends of the columns are fixed. So till here there is no bending. Till here there is no bending. After that the column bends. So you can see this is in the case of both the ends fixed. Suppose one end is fixed and other end is hinged. You can see here this end is fixed and this end is hinged. Okay, so till here, this because of this fixity there is no bending, and then it starts bending. Okay, that is in the case of one end is fixed and other end is hinged. And the last condition is one end fixed and other end is free. You can see here one end is fixed and other end is free. So fixed means till here it moves like this, then it bends. Okay, so this is all the 4 end conditions of the column. Now we'll see what is the formula for this. See, when both the ends are hinged, what happened? The bends, it's like this. So but the length remains same. So effective length is equal to L is equal to L only. But once they are fixed, what happens? Now till here this is same, it doesn't bend, then it starts bending. So effective length is equal to L divided by 2 here. Next, in the case of one end fixed and other end is hinged, here this is fixed and this is hinged. Okay, so what happens? Effective length is equal to L divided by root 2. And one end is fixed and other end is free. Here one end is fixed and other end is free, so length becomes 2L, this effective length. So this you should know, Euler's formula and equivalent length of a column. So based on this theory, the Euler derived the equation PE is equal to pi square EI divided by LE square, where LE is the effective length, or it is equivalent or effective effective length of the column. So the effective length of the given column with the given end condition is the length of an equivalent column of the same material and cross section with both ends hinged and having the value of cripping load equal to that of the given column. Thank you.